Can you enable screen sharing or give me host?
All right, got it.
Okay, everyone. So today we will be going over the very basics of combinatorics. So we'll be going over some really basic stuff, and then we'll go briefly into permutations and combinations.
And basically, if you never study combinatorics, what is combinatorics? So basically, this is the number of ways to count things. By studying combinatorics, you learn the fancy ways of counting fancy numbers. For example,
what do you mean by fancy numbers?
Well, for example, combinatorics allows you to solve this problem right here. Bob is getting dressed in the morning. He has 5 different shirts and 5 different pants. How many unique outfits can he put together?
That's really easy.
By studying
25.
combinatorics, you will be able to solve this question.
That's very easy, 25.
Yeah, so we have 25 different total combinations, right? Do you know what that is?
I got it from 5 times 5 because there's 5 different pairs. So there's 5 times 5, which is 25. That's the answer.
That's right. But for the people who doesn't know combinatorics yet, Jonathan, do you want to draw a combination tree, like a 5 different shirts branching out to 5 different pants?
I got 5 different colors, sure.
Advanced drawing.
I'll draw a shirt.
You can just draw like shirt 1, shirt 2.
As a shirt. So we have, I'll just draw circles for now. So we have white, you have blue different shirt. So for each one of these shirts, we have 5 different options for pants, right? So that's why we have 5 times 5 here. So if I were to draw all these different shirts, and I can branch them out. So this would have 1, 2, 3, 4, 5 different pairs of pants, right? Again, all of these colors, and the same thing would be for each one of these. So does that make sense, everyone?
Yes.
So again,
All right,
here
then
the blue would
let's-
have 1, 2, 3, 4, 5. So you count all these up, you get 25 different.
All right, I think we all get the gist of it. So why don't we go on to the second slide?
Okay, so this is a slightly more challenging problem. So if I were to have 6 different pairs of socks and 2 different pairs of shoes, in addition to the 5 different t-shirts, how many outfits can I put together here?
This is slightly harder than the previous one. Loy says that it's 60, huh?
I also say it's just.
Okay, does anyone want to explain their reasoning? Loy or Kimmy, do you guys want to explain where the 60 came from? Look, Kimmy, go ahead.
6 times 2 times 5.
All right. Okay, so as before, why don't we draw the combination tree real quick just to see the logic behind it.
Okay, so I'll just draw circles for socks. We have 6 different pairs. I'll just number them for now. 1, 2, 3, 4, 5, 6, right? And for each of those pairs of socks, we have 2 different pairs of shoes we can go with. So this would be 1, 2, 1, 2, 1, 2, and so on, right? And then for each of these possible combinations of socks and shoes, we have to choose from one of 5 different t-shirts, right? So again, branching off again. So each one of these would have 5, and that would go down for all of them. So that's where we get 6 times 2 times. So we have 6 different socks here, times the 2 different pairs of shoes, and then times 5.
I'm there.
You watching videos, Lloyd?
Eric, can you mute your microphone?
Sorry.
All right, so are there any questions for this? If not, we're gonna go to the next slide, which are gonna be a slightly different concept. Kimmy, your hand is raised. Do you have a question?
Oh, nothing. It
All
got
right, then.
raised.
If we don't have any questions, let's go on,
Because
Jonathan.
there's an updated thing where if you hit it detects your hand motion. So when I put it up, the thing automatically goes up.
All right, Jonathan is selling ice cream. Jonathan sells ice cream 3 balls to a cone. if there are 5 different flavors of ice cream, how many different combinations of balls are there? Note that the order of the balls from top to bottom matters. So it'll be something like this. 3. And we want to find out how many orders of balls there can be. As Jonathan has drawn.
Balls.
Okay, so
Can
this
I
time,
try this? Can I try this?
oh, you want to give it a shot for the problem?
Yeah.
Yeah,
So
go ahead.
5 times 3,
Mhm.
15. 5 times 5 times 3.
So 5 times 5 times 3.
Yeah.
Okay, so why'd you do the 5 times 5 times 3 here?
Oh, I do that again. 5 times 5 times 5.
Oh,
times
that's what I
3
mean.
times
Okay.
3 times 3.
Yeah, 5 times 5 times 5.
Because like there's 3 layers. That means we have to have a bunch of a layer kind for every layer. And then 3 times 3 times 3 because it's same concept.
Mhm.
I saw your responses. You are on the right track. However, indeed, it should be 5 times 5 times 5. One way to think of this is that to think of it as like one of the previous problems. So this one is worded slightly different, asking you how many different combinations of ice cream balls are there, but you can think of it as in like how many options of the top ball are there, right? There's 5 different options. How many options of the middle ball are there? There's 5 different options. And how many layers of the bottom ball are there? There's also 5 different options. So if you want to, you can think of the top ball as a t-shirt, the middle ball as your pants, and the bottom one as your shoes. So you have 5 shirts, 5 pants, and 5 shoes, which using the logic from the previous problems would simply be 5 times 5 times 5. Does that make sense to everyone?
Yeah.
Yes.
Everyone got it?
All right, great.
5 to the power of 3.
Yeah, okay, now so we're going to go over something a little bit more complicated. So we're going to be going over the concept of factorials. So we'll start off with this little problem here. Bob has 5 different math textbooks. So how many ways can Bob arrange his 5 books on a shelf? So assuming that order matters, we're going to say we're going to go from left to right. So he has to arrange his books. Anyone have an idea of how to do this?
I'm guessing, but I'm guessing it's 25.
25? Not quite.
though.
Anyone else have an idea for this problem? Okay, so here's where the concept of factorials kick in. So the way that this problem differs from the other problems earlier is that after we pick up one of the books, we no longer have 5 books. So for our first choice, we will have 5 books, right? But for our second choice, we no longer have 5 books because we just put one of them on the shelf. So now we can only choose from 4 books, right? So for the second time, instead of multiplying by 5 again, we multiplying by 4. And then so on. The third time, we have 3 books left, then 2 books, and we only have 1 book left. So this is for each choice. Here's the first choice. Here's the second choice. Here's the third choice, fourth, and fifth. So what we just did here, this is equal to 5 factorial. So here's the notation. We would write a number and then exclamation mark, and that just pretty much means you're going to multiply the number and keep going down until you reach 1. So this is for problems like this, where after you choose something, you take that away and you put it somewhere else, and you can only choose from one less of that. Does that make sense?
One way to think
Yes.
of this is to also think of it as like t-shirts and pants, because you can think of it as there's 5 slots. Jonathan, can you draw 5 boxes in a row?
You mean there's 5 boxes? How can you order 5 t-shirts?
Right. So what you're trying to do is you're trying to put the 5 books in the 5 slots, right? You're trying to order them. And so you can think of the leftmost slot as your hat. And you have 5 hats. And for your second box, it's your t-shirt. However, since you only have a total of 5 books, you can think of it as you have a total of 5 pieces of clothing. This analogy may seem a little weird, but in this analogy, you would only have 4 t-shirts. So you would have 4 options for the second box or your second slot. And then the third slot would have 3 pieces of clothing. You can think of it as your pants because you only have 5 books in total and you already used 2 of them on the first and second slots. So for the third box, you only have 3 choices of which book to put. And similarly, the second to last box will be a 2. And finally, the last box is a 1 because all of your 4 books have been used. You only have one book left, so you have no choice but to put it in the last slot. So combinatorics in general, you want to think of it as how many options you have of doing something. So to recap this, in the first slot, you have 5 different choices for which book you want to put as the first book. After that book, you have 4 choices to put at a second. The third has 3 choices, the fourth has 2 choices, which is why it ends up being 5 times 4 times 3 times 2 times 1, which Jonathan explained is equivalent to 5 factorial. Does this make sense to everyone? Are there any questions?
Yes.
Alright, cool. Everyone else, y'all got this? If it helps, I can draw a diagram here for the books.
All right, I think we get the gist. Why don't we try this Josh problem? It's very similar. Wait, Olivia has a question. The equation to the left is related, right? What do you mean by?
Yeah, here. So the equation to the left here where I wrote the little x thing, that's just explaining how a factorial works. So it's just saying if I had a number x factorial, then the factorial will be equal to the number times itself minus 1 and so on. So like here earlier up here, the x is equal to just 5. So if I wrote 5 factorial here, that's equivalent to pretty much 5 times 5 minus 1, which is 4, times 5 minus 2, which is 3, and then so on all the way until you get to 1. So does that make sense there? Hopefully it doesn't confuse everyone.
All right, it makes sense. Great. All right, Josh. How many ways can Josh stack his cups? Olivia, you want to try this one? How many ways can Josh stack his 10 cups of 10 different colors? No thanks. All right. Kemi, do you want to try this one?
Sure, I think I got an idea. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1.
Got it. So this is the same concept as before, right? Okay. So this is the total number of combinations we have because the first time we stack when we get the first cup stacked, we have 10 choices. And then once we stack that cup, we only have 9 cups left to choose from. And then after we stack that, we only have 8 cups left to choose from, and so on, all the way until we get down to here. That's supposed to be 0.
That's right. Because the number is kind of big, we're not going to calculate it. But hopefully you get the gist of what the factorial is. And all right, Olivia gets it. If there's any questions, please do ask us. But why don't we go on to the next slide, Jonathan? All right, so there are 7 Whittaker siblings. And for some reason, we're trying to get the siblings to sit in a row of chairs. So how many ways and how many different orders can those 7 Whittaker siblings sit in the row of chairs from left to right?
7 to the power of 7.
7 to the power of 7. Does anyone agree?
Because there is 7 Wheelan, that means there are 7 choices. That means there's 7 to the power of 7. Or it could be 7 times 6 times 5 times 4 times 3 times 2 times 1.
Yeah, it's the second one. Do you know why it's the 7 times 6 times 5 and so on, instead of just 7 to the 7th power?
Oh, I get it now, because once you place down one sibling, you have only 6 siblings.
Once you sit someone down, we only have 6 people to choose from, right? We don't have 7 people to choose from anymore. So it wouldn't be 7 factorial, it wouldn't be 7 to the 7th power here. It'd be 7 factorial.
Right. Why don't we draw the row of squares again, Jonathan?
Yep.
So in this problem, you can once again thinking of it as filling stuff inside slots. So in this case, you have 7 chairs, so you have 7 boxes to fill in. And you can think of it as a sibling by sibling scenario. So let's say that the eldest sibling gets to choose the chair first. So the eldest sibling, since no one's sitting in any chairs yet, has 7 choices for which chair he wants to sit in. So that gives us the initial 7.
Right? So if you have 7 chairs to choose from, so after this first person sits down, they take up a spot, right?
Yeah.
Therefore, when the second sibling decides to choose a chair, he only has 6 chairs to choose from. That means he only has 6 choices, which is why you multiply by the 6. After that, the third sibling only has 5 chairs to choose from. So he has only 5 options, which means you multiply by the 5. Similarly, the fourth sibling only has 4 chairs left he could choose from. So you'll multiply by the 4. And so on and so forth, all the way until you end up with the last sibling. The last sibling has only 1 chair to choose from. So you just multiply by the 1. Does that make sense to everyone?
That's why you should never be the last sibling.
That's right. All right, I think we get the gist of it. So why don't we move on to the next slide? All right, so we're going to move on to permutations. So permutations is basically factorials. However, it can be used to count something that's more general, because with factorials, you can only count the number of ways to order things, whereas with permutations, you can solve problems like the one on the screen. There are 20 people in a class. The teacher has to pick a class president, a vice president, and a treasurer. None of the students can hold multiple positions. So how many ways are there to choose the officers?
Yeah, actually, I'm gonna change the problem real quick. Instead of 20 people, I'm just gonna say there's 5 here. So in case we need to draw this out, it'll be a little bit easier. So anyone have a guess for how we can solve this problem?
Me. Let me guess. It is 5 times 3 divided by 5. No, 5 times 3, yeah, divided by 5, which means it equals 5.
That's a good
So that's,
guess.
there's 5. So what?
I don't think that's quite the case, Kimmy, because that means there's only 3 ways to choose them, right?
Hmm?
And I'm pretty sure there's more than 3 ways to choose the officers.
So let's think about this just from a logical standpoint. Let's draw a diagram here and work things out. So I'm going to draw the 5 people. Guess we'll do them in different colors.
Let me ask, why is there only 5 people in a class?
So I can draw all the people in the class.
Because it's a very prestigious private school that only has a total of 10 people per grade. So this class only has 5 of them.
So there's only 2 classes?
That's right.
That's gonna be like the best thing ever.
I know.
Like,
That's pretty much what this math circle is. You guys are enjoying like private classes. Okay, so back to the problem. Let's think about this just from a logical standpoint, right? So we need to pick the president here, the president, vice president, and the treasurer. So how many choices will we have for the president? Everyone.
5. Oh, so 5 times 5 times 5 divided by 3.
Not quite. You gotta think about it this way. So once we pick the first person for president, let's say we pick this guy over here, we can no
5
longer select
times
him.
4 times 3.
Exactly. We can no longer select him for the vice president, right? So we're choosing the vice president position. We have 4 people left to choose from. So that's when we multiply by 4. And once we select the vice president, we only have 3 people left to choose from for the treasurer. Like
The
that.
answer is 60.
Yeah. So as you can see, it's sort of like the permutations, sorry, sort of like the factorials we talked about, right? Or we're going down one by
That
one.
means every person has a 60% chance of getting into there.
Yeah. But you can see how this is sort of similar to our factorials, right? We're going down one by one. The difference here is we don't go all the way down to the last one because we don't have that many positions we're looking for. We're only looking for 3 people out of the total of 5 people in the class.
Why don't we try it with 20 people?
Yeah, so how
That
do we do
means
this with
20,
20 people?
19 times 13. 20, 19, 18, right?
It's 20 times 9. So if there were 20 people here instead of 5 people, then the first one we have 20 people to choose from, and then 19, and then 18. All right, so does everyone get this concept here? This is a pretty important one for combinatorics.
So far, it's quite easy.
Yeah, I think we all get the gist. Let's move on.
Okay, cool. So here is the pretty much what you guys just came up with, right? So this equation here looks kind of scary, but it's the exact same way, same thing that we just did. So here,
Oh.
yeah, so
can
we're gonna
basically
tackle this problem here using that.
you can basically think of it as, Olive, I'm going to explain it right now. So what NPR notation means is that you're trying to choose R officers from N people. So for example, you're trying to choose a class officer, a class president, a class vice president, and the number of officers you're choosing is exactly R. And you're choosing these R officers from a total of N people. So in the previous example, we had 5 people in total, and we're trying to choose 3 officers, a president, a VP, and a treasurer. And we ended up with, remember, 5 times 4 times 3. So if you plug it into the formula, it's basically equal to 5 factorial over 5 minus 3 equals 2 factorial. And remember, 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. So when you cancel it out, it's just 5 times 4 times 3.
So this is pretty much what we just wrote. We went from here, right? Oh, patch that up. Okay, so Olivia, to answer your question, the exclamation marks are it's just to say factorial. So if I write like a number, let's just say 3, and I put an exclamation mark behind it, what I'm looking for is that number, and then I'm going to multiply it by itself, or like multiply down to 1. So if I have 3 factorial here, it'd be 3, and then multiply by 2, and times 1. If I had 5 factorial here, so exclamation mark, it'd be 5 times 4 times 3 times 2 times 1. Does that answer your question?
All right, yes, great. So how many different ways can we get a list of 5 songs from a playlist of 15 songs? So we want to choose 5 songs from a playlist of 15 songs, where the order does matter. So how will we tackle this problem?
Doesn't this mean 15 times 14 times 13 times 12 times 11 times 10?
Does everyone agree with that? Lloyd, Joyce, Olivia, do you guys agree with what Kimmy said? Lois says yes. Olivia, what do you think? Do you think this is correct? Maybe. All right. Why is there the uncertainty? What are you not sure about? What makes you doubt the validness, correctness of this answer?
She's probably just gonna say because he sometimes is wrong.
All right. This is indeed the correct answer. Kimmy, do you want to explain how you got this?
You want to explain this using the logic we went over earlier for the last question here? Remember
Okay,
the
I'm ready.
5 people in the class.
Yeah, it's kind of like that. Just since there's 15 songs, there's 5 places. Place all the songs. Once we place one, there's only 14 left. Yada yada.
Yeah, so when we're picking the first song to add to our list, right? Out of the 15 songs, we have 15 choices. And then once we pick one of them, we can't pick that same song again. So now we have to move on and then pick 14. We have to pick out of the 14 songs remaining, and then the 13 songs remaining, and the 12 songs remaining, and then the 11 songs remaining. And we stop here at 11 because that's where we get our 5 songs. You have 1, 2, 3, 4, 5 choices. And then again, if you use our equation here, a little formula up the top here, it's the same thing, right? We have 15 factorial divided by 15 minus 5 factorial. This is quite a big number, but if you write all this out and cross cancel, you'll find that you get the exact same thing here.
And one thing to say about this formula is that although we do let you know what the formula is, you honestly shouldn't know this formula. Like, you shouldn't use it on a regular basis. When you see a problem like the one on the screen, how many different ways can we get a list of 5 songs from a playlist of 15 songs? What you should be thinking about is 15 choices for the first song times 14 for the second, times 13 choices times 12 times 11. You shouldn't be thinking about, okay, n equals 15, r equals 5. Let me plug into this formula and get 15 factorial over 15 minus 5 factorial. You shouldn't be thinking like this, because what's important of combinatorics is that you want to understand how we got these formulas. And when you understand how things are derived from, you have a much better understanding and grasp of the concept, rather than just understanding what the formula is. I mean, remembering what the formula is.
Yeah, if you do math counts in the future, like the AMC, using your just basic logic to figure out this problem instead of just plugging everything into the formula will usually be faster. So that's another reason why. This here is just for you to know it, I guess. Don't depend on this formula.
That's right. All right, I think we get this. Let's move on to the math example, which will transition into the burger example. All right, how many rearrangements of the word math are there? For example, ATMH is a rearrangement. Hat M is a rearrangement. So how many rearrangements of the word math are there?
I think I know. It's math. It's 4! Exclamation mark.
4 factorial.
Yeah.
Do you want to give us your reasoning?
I was like, math, if we do 4 times 3 times 2 times 1, it's basically like it. We choose 1. Like the first one. We have 4 spots. We choose 1. We only have 3 left. We choose another one. We only have 2 left. And then etc.
Yeah, you got it. Everyone else understand this logic? Here.
This one, I indeed have to say it is very tricky.
Yeah, so this is like this pretty much the same thing as our other problem, but here we're doing it with letters instead of the previous example, which was songs. So this problem is pretty straightforward, right? We have all different letters, so they're all unique. We just count all of them and we're done. But what if we tackle this next problem here, which is the rearrangement of the word burger? So how do you think we can do this one? Lloyd, Joyce,
That is
Olivia,
pretty
anyone have
easy.
any ideas?
That's pretty easy. Right?
Well, Kimmy, there's a twist to it.
Isn't it 6 times 5 times 4 times 3 times 2 times 1?
Well,
Not
that
quite.
would be the case for another example, but the thing is, notice that the word burger has 2 R's.
Oh, so it's 4 times 3 times 2 times 1. 5 times 4 times 3 times 2 times 1. I see the twist now.
That's a
Mhm.
good.
If you
Yes.
treat it just by writing like 6 factorial here, everyone, if you just treat this problem like the previous one, you would actually overcount because you're treating the 2 R's like they're unique when in reality they're not. So the question
In
would
fact,
think,
to demonstrate what Jonathan is talking about, we're gonna do this little exercise here. So instead of just writing the word burger, we're gonna call it B capital R ger, and the other R will be a lowercase r, like this. So let's do a couple of rearrangements. So for example, one rearrangement is let's say RUBGER, like this. But another
Bugger.
rearrangement would be small r UBGE big R. And in this, sorry, the other E should be capitalized. Let me read you this real quick. All right, so as I was saying, that one example will be RUBGER. Well, the other one is small r UBGER. And indeed, it looks different because the capital R's and lowercase r's make the words different in your eyes. But remember that the big R and the small r in the original problem are both just regular R's. So in reality, you wouldn't know that there's a difference between these two arrangements. They would appear the exact same, and therefore they
means
would
it's
only
5
count as one
factorial.
arrangement.
That means it's 5 factorial because we just cancel out the both R's to make them 1 R.
Well, that's a
5 factorial.
good guess. However, the thing is, if you only count them as one R, then that means you're only doing a rearrangement of the word bugger. You're not doing a word arrangement of the word burger, right? Because there's 2 R's. So if you just ignore the other R, you're doing a different
Yeah, I
problem.
feel like we should do an arrangement on booger.
we'll see if you're just gonna treat it like 5 factorial here, you're only doing 5 choices. So like Hambo said, you would be losing 1 letter. We need to treat this problem with 6 choices because of the 6 letters, but we have to get rid of the times we're counting extra for the 2 R's because they're the same.
Or to use some more fancy combinatorics terms, you want to correct the overcounting. All right, to solve this example, you would start with 6 factorial because you will pretend that you're actually rearranging the word burger where the other R is a lowercase r. So if these 2 R's were different, you would have 6 factorial as Jonathan has written on the screen. But then, as we have just demonstrated, when you do this example, you would get double arrangements like this, RUBGER. These, when you arrange burger with a small r on the end, you would get 2 arrangements. But in reality, these 2 only count as one arrangement of burger because when you change the small r back to the big R, they are the exact same rearrangement. So in other words, we can realize that when there's 2 R's, there is a copy of every possible rearrangement,
Wait,
which means you would simply divide by the number of copies, which is 2.
Yeah, so or you can also subtract 2 twice, right?
You would actually subtract. I don't think subtraction works here because what's happening is that every arrangement is getting doubled. So you want to divide by 2. Yeah.
Oh, I see why. I see why. Okay, I see
Yeah,
why.
in other words, no matter what arrangement you do, there's going to be both r's in here. And then if we just do 6 factorial, every single arrangement, which includes 2 r's, will have both versions of it, where there's goes capital R first, then lowercase r, and lowercase r, then capital R. And then those two are actually the same because in reality, the 2 r's are both capital. So that's why we need to divide by 2 because the number of rearrangements we counted are actually doubled.
All right, before we go on to the next example, why don't we do a variation of this problem? So now instead of rearranging the word burger, why don't we rearrange the word
Booger.
no, let's rearrange. Wait, actually, we'll go into booger maybe later, but right now I want to do the word Alabama.
Really?
Well, yes, because in this case, know that there's 4 A's. So how would you rearrange?
So I get it now. This is starting to make sense. So it's how many letters is it? 3, 4, 5, 6, 7. So it's 7 this divided by 4. 7 factorial divided by 4.
You are on the right track. However, the thing is, it's not quite just 4 because the thing is that the 4 A's don't simply translate into 4, right? It actually translate into 4 factorial. And I'm going to show you why right now. So pretend that instead of rearranging Alabama, we're actually rearranging this. Jonathan, I'm gonna write it like this because like coloring is gonna take like a long time. So you can just like chill for a bit. I'm gonna type this. So let's pretend that we're actually rearranging 1L, 2B, 3M, 4. All of the numbers represent the letter A. We're just like giving them a temporary distinction. So if we rearrange this, we would have
identity.
like, for example, if we just put all the letters in the front, LBM, 1, 2, 3, 4, there are actually a bunch of other arrangements that would look the same, but aren't quite the same, such as LBM1, 2, 4, 3, LB1, M2, 1, 3, 4, 2, or LBM 1, 3, 2, 4. And you would actually end up with 24 of these arrangements because you would have to go through all of the combinations of the ordering of the numbers.
Does that mean the answer is actually 7 this divided by 4 this?
That's right. It's 7 factorial over 4 factorial because
I get it now because there's 4 and then you could erase from 4 and 3 and 2 and 1.
That's right, because let me finish my explanation real quick. Because when you type all of these different possible rearrangements, and by the way, as I have mentioned, there are total of 4 factorial equals 24 of them. And why is it 24? Well, this goes back to the very first examples that we went over. You have 4 numbers and you want to arrange them in different orders. How many ways can you do that? That's 4 options for the first, 3 options for the second, which is 4 times 3 times 2 times 1. So there's 24 of these, but remember 1, 2, 3, 4 all corresponds to the letter A. So when you swap these numbers back with the letter A, you just get LBM A. So all 24 of these arrangements actually are equal to 1 arrangement. So that means for every valid arrangement of Alabama, you actually counted 24 of the copies of that arrangement, which means you have to divide by 24, which is why, as Kimmy has said, that number of arrangements of Alabama is actually 7 factorial over 4 factorial to account for the overcounting. Does that make sense to everyone?
Yeah, this is a lot to take in. So if you have any questions, please feel free to ask it.
Does that mean we could write it as L B M A A L B M A. We could write it 4 times as A, right?
It doesn't quite get it, so I'm gonna explain this real quick again. Let me clear all of this real quick. All right, so Olivia, let's say that we're trying to arrange the word Alabama, right? And let's say that instead of just counting the Alabama, we're actually counting 1L, 2B, 3M, 4. So we're basically swapping all of the A's with distinct numbers. So instead of just 4 identical letter A's, we actually have 4 different numbers, so we can distinguish between them. So if you were to rearrange this peculiar configuration of letters and numbers, you would have, for example, LBM 1, 2, 3, 4. You could also have LBM 1, 2, 4, 3. You could also have LBM 1, 3, 4, 2 or LBM 1, 3, 2, 4. And you could also have LBM 1, 3, I don't know, 1, 3, 1, 4, 2, 3, LBM 1, 4, 3, 2. And the list goes on and on. And the number of arrangements that start with LBM and with all numbers, there are actually 24 of them, because if you remember what we talked about at the beginning of class, it's like you're trying to rearrange the number of books on a shelf. You have 4 options for the first book, 3 options for the second book, 2 options for the third. So it's 4 times 3 times 2 times 1. And it's the same thing with these numbers, because we're basically doing a reorder of these numbers. So indeed, there's 24 of these rearrangements. However, the thing is, remember, Olivia, what we did was we swapped all of the A's for these numbers. These numbers are actually the exact same letter, right? So all of these rearrangements that I just typed out actually all correspond to the rearrangement LBM A. That means all 24 of these arrangements actually correspond to one valid arrangement. So when you count all 24 of these, you really should be counting 1. That means if you do 7 factorial, you counted the number of arrangements of Alabama times 4 factorial, right? Because as I have stated, every single rearrangement of Alabama is counted 24 times. So therefore, you have to divide by 4 factorial. Does that make sense?
Yeah, so in other words, remember, we're starting off with the 7 factorial on top because there are 7 different letters, right? So when we're arranging them, we start off with 7 choices and then 6 and then 5 and so on. We multiply that together. And then for every single combination that we make of the word Alabama, we have to include all 4 of the A's, right? So in Hambo's example, where we started with LBM, AAAA, all 4 A's are included. And then when we do 7 factorial, it actually counts the A's like they're differently. So 7 factorial here assumes that we have 7 unique elements, but in this case, 4 of them are repeating. And those 4 that are repeating get overcounted. Hambo here gave the few examples of here. Because there's 4 of them, there are 4 factorial ways to count them. Right? So for every iteration about every way of spelling this word Alabama, no matter what it may be, there's 4 factorial ways to arrange the A's in that word. But the A's are all the same, so we actually need to get rid of those extra counting, and that's why we divide by the 4 factorial.
I have something weird to ask.
Mhm.
What if the word is B-O-O-O-O-O-O-O-O? B in 4 O's. How do you count that?
We will do that after we explain this real quick. It's pretty similar. So Olivia, do you get that? Okay, cool. So let's move on to Kimi's example here, because that's actually a pretty good example. So Hambo, can you clear the board real quick?
Oh yeah, of course. Let me just type great to Olivia real quick. All right, clear the board.
Okay, so we're gonna go with Kimi's example of boo here.
4 O's.
Yeah, so again, how many different letters do we have? We have 1, 2, 3, 4, 5 letters, right? So when we're arranging them, we have 5 different choices for the first one, 4 different choices for the second letter, and so on. So the total area range of these letters here is 5 factorial. But remember, every single iteration or every single arrangement we have of these includes these 4 O's. And these 4 O's are all the same, but when we do 5 factorial, we treat them like they're differently. So when we do 5 factorial here, it's the equivalent of saying B 1, 2, 3, 4. Or since we're sticking with the letters here, it's equivalent of saying BA, oh, not BA, I say,
WXYZ.
yeah. Right. So 5 factorial treats them like they're all differently. But remember, no matter how we do this, this W, X, Y, and Z are all O's. So, W, X, Y, Z, X, Y, W, Z, these are all the same. So we have to divide by those arrangements. And then because there's 4 O's here, there are 4 factorial ways to arrange them, right? Or I shouldn't say the O's since they're all the same. W, X, Y, Z, these 4 letters, there are 4 factorial ways to arrange them. So we divide by that much because that's how much we're working on.
All right. Hopefully that makes sense to everyone.
Okay,
Why don't
so
we go
that
into
works. But what if so it is the number divided. It's the number of total by number of letters total factorial divided by the number of repeats factorial, right?
Yeah.
But what if there is no other number? Oh. So is it 4 factorial divided by 4 factorial?
That's right. If there was only one type of letter and then higher word like 4 O's, then no matter how you arrange it, it would always look the same, right? So you will only have one arrangement.
Oh.
All right. Why don't we go on to the next example? So basically, that was an introduction to combinations. In combinations, we do not care about the order. Combinations is the number of ways to choose elements from a set to form a subset where the order does not matter. For example, if I was to choose what toppings go on my pizza, I wouldn't worry about what order I put the toppings on my pizza, right? Like it doesn't matter if I put the mushrooms first or if I put the pepperoni first. The wording might sound a bit confusing, but the next example will clear it up.
Imagine the next example is booger.
So remember how we started with the example of choosing a president, a vice president, and a treasurer from a class of 5 students, right? Well, in this class, we're trying to form a small committee of volunteers. So we have 15 students and we're trying to choose 3 volunteers for the committee. And note that it doesn't matter what order we choose the volunteers because they all end up as simply volunteers, right? There isn't such thing as like a president or a vice president. All of the volunteers are the same. So how many ways can we pick the 3 volunteers? Go ahead, Kimmy.
I want to ask a question. What if the word is Butterfingers? Like if it has 2 doubles.
That's actually a great question. Since Kimmy raised the question, I guess we should go on a bit of a sidetrack.
We'll do it on
Like
the slide.
Butterfinger, it has 2 B's, 2 F's, 2 T's, and also 2 F's.
Well, how's there 2 F's? Am I missing something? There's 2 E though, so it's 2 E, 2 R, there's 2 T's.
Yeah.
Okay, so
2 E's,
let's
2 R's, and
first
2
off, let's start off by going over which letters here are repeated, right? We have repeats of the word of the letter T. There are repeats of the letter E. Repeats of the letter R. Right? So how many repeats do you have each? We have 2 repeats of the T, 2 repeats of the E, and 2 repeats of the R. So solving this one would be pretty similar to the other ones, right? We find the total number of combinations, assuming that every single letter here is unique. So how many total letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're going to assume that each of these 12 letters is unique. So we start off with 12 factorial, right? But then we overcount because we're assuming that the two t's are different, the two e's are different, and the two r's are different. So we have to divide by those. So this would be pretty similar, right? Go with.
Does that mean fact blank the number of whole letters factorial divided by 2 factorial divided by 2 factorial divided by 2 factorial?
Pretty much.
Right.
Yeah,
That is
so everyone get that? Same concept as earlier. We're just dividing by how many times you overcounted. Because again, we have the two t's, the two e's, and the two r's. We're just doing it the same. The 12 factorial here assumes that everything is different, but everything is not different. There's two t's, two e's, and we have to divide those out.
Olivia gets it. Very good.
Cool, yeah, so
Congratulations.
this combination stuff is pretty hard. You guys will probably learn it like middle school or yeah, probably sometime middle school. So you guys are getting a head start on this.
All right. So going back to our little committee. So we have 15 students and we want to choose 3 volunteers. And remember that it doesn't matter which order we choose the volunteers because we no longer have a distinction between the officers, right? Remember before there was a distinction of the president, the vice president, and the treasurer. In this
Yeah, but
case,
now
they're
they're all
simply
Butterfinger.
volunteers. So how many ways can you choose the committee?
Now if you volunteer, you're gonna be a Butterfinger. If you volunteer in any one of them, you're a Butterfinger.
All right, so anyone have a guess for this? Joyce, Olivia, Loy, you guys got an idea?
Is it 5? Oh wait, no, never mind. Is it 15? Wait, let me write it down. It's 15 factorial. 15 factorial divided by 3 factorial.
That's actually an excellent observation based on what we just learned. The bottom part is absolutely correct, but I'm not really sure about the top part. Are you sure it's 15 factorial? Remember that we're only choosing 3
15.
volunteers.
Is it 15?
Well, there are 15 students, but we got to keep in mind how many we're choosing, right? So this is sort of a culmination of all the stuff we learned earlier. How many people are picking? We're only picking 3 slots. So how many would be on top? The 15 factorial that you said earlier, that assumes that we're going to pick 15 slots because that's 15 choices we're making. But we're only going to make 3 choices. So how much would that be?
You know the bottom is 3 factorial.
Right.
And what is the top?
Anyone want to help them out here? This is pretty much like what we went over earlier.
5 factorial.
Not quite.
Well, why don't we
3
think about it like
factorial.
this? Kimmy, since you divided by the 3 factorial, that means the top is overcounted. So in the top, we're pretending that the order does matter because we're dividing by the order on the bottom. So how many ways are there to choose the first volunteer?
15 factorial.
No, Kim, we're only picking the first volunteer, the first person.
And there's 15 choices.
Right, so the first person, there's 15 choices to pick the first person. And now that we pick one
15
volunteer,
times 14 times 13.
that's right.
Everyone
So-
else got that? So remember, we only have to pick 3 people here. So 15 people for the first choice. Then after we pick one of them, there's only 14 left. So there's 14 for the second choice and then 13 for the third choice. But then here again, we're assuming that they're all taking different positions, but they're all having the same slots for the committee. So we need to divide by 3 factorial because that's how many ways we can arrange the 3 people in those 3 slots.
I
right.
completely understand.
That's great, Olivia.
Yeah, cool. If you guys actually
And-
understand this, that's
There's
Pretty big
actually
jump.
like a really cool way to think of this too. So one way to think of this is that you're rearranging the word S, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, S, V. So you want to find the number of arrangements of
Oh,
S
standing
S
for
S V V
15
V.
people. Is it standing for 15 people?
Yeah, there's 15 people here, right? But you notice how a bunch of them are S and some of them are,
Oh.
oh,
Oh well, actually, now that I think this isn't really an adequate example because you would also have to divide by the 12 factorial. But what I was trying to convey is that basically it's like rearranging the number of orderings of a word, except you have to overcount. You have to account for the overcounting the ways that it's repeated, right? Because one way you can think of this problem is you want to start off by choosing a president and then choose a vice president and then choose a treasurer out of the 15 people. But then for some reason, the teacher decides to call all three of these officers just volunteers. So they end up being equal people. So no matter the order that you choose the officer, the president, the vice president, and the treasurer, they actually all end up being the same thing. So for example,
Spiderweb.
let's say that I chose Kimmy to be the president. I chose Joyce to be the vice president, and I chose Olivia to be the treasurer. So I end up making everyone volunteers. So Kimmy is a volunteer, Joyce is a volunteer, Olivia is a volunteer. But now let's say that I chose Olivia to be the president. I chose Joyce to be the treasurer and Kimmy to be the vice president. And then I make everyone volunteers again. So Kimmy is once again a volunteer, Joyce is once again a volunteer, and Olivia is once again a volunteer.
That
So
means
notice
there
how
is no change.
exactly. So notice how the way the order that I choose you three people doesn't matter in the sense of forming a committee, because in a committee you don't care about the order. Exactly, Olivia. So that's pretty much an introduction to combinations. And a fun fact is that you guys all have heard of combination locks, right? A combination lock is like you enter 3 digits and you unlock the lock. However, that is actually incorrect, because a combination lock means that you're simply choosing 3 digits. It doesn't matter what the order of the digits is. So it could be 135, it could be 315, it could be 1513. But a combination lock, in reality, it actually does matter what the order is. Like if the combination password is 135, you can't put in a 531 and unlock the lock. So a more adequate name for our combination locks is actually a permutation lock, because in a permutation, the order of the numbers actually do matter. So you can go tell your teachers that the combination locks is actually named incorrectly. But that's all we've got for today. We did an introduction of permutations and combinations.
Can we do the word?
Pardon, Kimmy?
Can we do the word? Let me see. Can I? Wait, give me a second.
yeah, but for everyone else here, thanks for coming. That was a pretty hard lesson, so good job getting through that. The discussion problem will be another sort of problem, like combining everything we learned today. And then next week, we'll be doing some more interesting puzzles related to combinations.
Could
Yeah, thanks for coming, everyone.
the word of godness